In this video, I want to provide a second derivation of the prior predictive distribution for the circumstance of where we have a Poisson likelihood and a gamma prior. So the method we used before was based on the fact that the probability of a data point x is itself a marginal probability density, and we actually found the marginal probability density by integrating out over all choice of theta the joint density of the single observation x and the parameter lambda integrated over all choice of lambda. And then what we did is we used the conditional probability rule to decompose this joint probability into the probability of x given lambda times the probability of lambda integrated over choice of lambda. And when we write it like this, we notice that this first part here is the likelihood and this second part here is the prior density. And we were able to, via a sort of neat trick, actually calculate this integral. And as it turns out, we found that this sort of prior density, when I sort of multiply it through by the likelihood and integrate, the prior predictive distribution turns out to be something which we call negative binomial. It turns out that there is actually another method that we can use to derive the prior predictive distribution which doesn't rely on us actually doing an integral, and it's this method which is particularly useful and perhaps easier for circumstances of when we're talking about conjugate priors. And the way in which we actually find this is by a rearranging of Bayes' rule. So Bayes' rule, just to recap, is that the probability of lambda given this sort of data point x, the single data point here, is equal to the likelihood, the probability of x given lambda times the probability of lambda, which is just our prior, divided through by the probability of our data point x. And when we write it like this, we see that the denominator here is that which exactly we are trying to get. So if we rearrange Bayes' formula for this particular probability, then our job is done. So what we can do is we can rearrange this such that we get that the probability of x is equal to the probability of x given lambda times the probability of lambda, all divided through by the probability of lambda given x, in other words the posterior. And because we have the posterior and because we have the prior and the likelihood, we can just substitute in each of these results, and we should also hope to get the same result, which is the fact that the prior predictive distribution is itself negative binomial. So if we substitute in each of these individual bits, we find that the probability of x is equal to, well, the likelihood in this particular circumstance is just lambda to the power x times e to the power minus lambda, all divided through by x factorial. That's just the Poisson likelihood. And the prior here that we've chosen is a gamma prior, which has got a form of beta to the power alpha divided through by the gamma function of alpha times lambda to the power alpha minus 1 times e to the power minus beta lambda. So that's our numerator. Then all we need to do is just divide this through by the posterior density, which we know in this particular example is just 1 plus beta to the power, in this case, x plus alpha, all divided through by gamma of x plus alpha. And then we multiply this through by the kernel, which is all those terms which depend on lambda. So we've got then lambda to the power x plus alpha minus 1, and then times e to the power minus 1 plus beta, all times lambda. And the reason that we've got this particular posterior, which looks slightly different to the one which we derived before, is that we've just got a single data point x here. Remember, before when we were doing it for a vector of data points, we actually had n x bar. Well, we see that in the case of when we've got just a single data point, n x bar is just equivalent to x. So this is exactly the same result as we got before. It's just a slightly different posterior because we're just considering a single data point x rather than a vector of data points. Then what we can do is we can start to cancel those terms which depend on lambda, because remember that we should get a density which is independent of lambda, so we need to check that that's actually the case. Well, we notice that if we were to take this lambda to the power x and multiply it through by lambda to the power alpha minus 1 on our sort of numerator, then we'll get a term which is exactly the same as lambda to the power x plus alpha minus 1, which is that which we have on our denominator. In other words, they'll just cancel. so we can get rid of these sort of lambda terms here. And then if we do the same for e to the power minus lambda times e to the power minus beta lambda, then again we're going to get the same as on our denominator here. So those sort of terms are going to cancel as well, just as we'd expect them to. Then what we can do is we can sort of rewrite this thing, and just perhaps in a sort of slightly neater form, as beta to the power alpha all divided through by 1 plus beta to the power x plus alpha. So that's just this part of the numerator divided through by this part of the denominator. And then we're going to have this times, we've got on the sort of top here, we're going to have gamma of x plus alpha, and on the denominator here, we're just going to have x factorial times gamma of alpha. And we noticed here that we can actually rewrite this sort of first part here as beta over 1 plus beta all to the power alpha, because both the top and the bottom of this first part of the expression have sort of alpha or to the power alpha in both of them. And it's this times 1 over 1 plus beta all to the power x in this case. And we recognize this second expression here in our marginal density as just being equivalent to our sort of expression of NCR. And in this example, we're talking about, if we were to sort of write it in its compact form, this is just equivalent to x plus alpha minus 1, all sort of as a sort of numerator of our NCR term, and x as being the denominator. And this, in sort of written in this form, defines exactly that which we obtained before. In other words, a negative binomial distribution in x, which is parameterized by alpha and, in this case, beta. So just to summarize, in circumstances when we're dealing with conjugate priors, we can use Bayes' rule to help us derive the prior predictive distribution in a way which is generally faster than actually carrying out the integral itself.